Okay, I'm going to do a short introduction to antiderivatives. So what we're going to do here is we're going to find the derivative of a couple of functions, and what's going to happen here is they're going to all differ by a constant. So they're just going to have some sort of constant. So we're going to pick on a fifth degree polynomial with just some different constants attached to it. And so by the power rule, the 5 is going to come down and subtract 1 from your exponent, and the derivative of the constant is going to be 0. And what we're going to find is each one of these has the same derivative. And when we want to do the antiderivative, we want to go back. We want to find what function that would have been. Well, these all have the same antiderivative. So I don't know which, I'm sorry, these all are the same derivative. I don't know which antiderivative they came from. So there's something lost when we take the derivative and then we want to go back. And that's going to be called our constant of integration when we go backwards. Now, a lot of problems will have some sort of initial conditions. You know, what do you start now with? A certain height or some sort of property that we know a certain position, and we can use that to find the constant of integration, and we'll find the particular solution. So our general solution would just be x to the fifth plus some constant of integration would be our antiderivative, and I don't know what that is. And we're going to look at a theorem in a minute. First, we're going to give the definition of an antiderivative. So an antiderivative f of a function f on an interval I and this is a function such that when I take the derivative of big F, it's going to be equal to little f of x, and that's going to be for all x in that interval. And you saw that each one of those original functions that we had when I took their derivative, I got that 5x to the fourth on the previous slide, and so those would all be antiderivatives. And we're going to look at a theorem here that says that if I have two antiderivatives of the same function, then they're going to differ by a constant. Okay? And this is an if and only if proof, so I'm going to have to prove both directions. So two antiderivatives, f of x and g of x, differ by a constant. Okay? And we'll say, we're going to say that f of x and g of x are antiderivatives of a function f on the interval I. And we're going to say if and only if f of x is equal to g of x plus a constant for some for some c in the reals, and then f of x is going to equal to g of x plus c for all x in I. So they're just going to differ by some sort of constant. Okay. Okay. So the first thing we're going to do is we're going to suppose that f of x is an antiderivative, and f of x is equal to g of x plus c, and we want to show that g of x is an antiderivative of little f. That is, if I take the derivative of g of x plus c, so we need to know it's differentiable, and its derivative is equal to little f. Well, I know that I can take the derivative of f of x, big F of x, and I know that's equal to little f of x. And so this tells me that g of x is differentiable because it's equal to a differentiable function plus a constant. So g prime of x is also going to equal little f of x. Thus, g of x is an antiderivative of little f of x on the interval I. Now the other direction is a little trickier. What we want to do is, and this is kind of a common trick when we want to show two things are equal, is we're going to take the difference of them. So we're going to do f of x minus g of x, and I want to show that that's equal to a constant. And if I can do that, then I just add g of x to both sides, and I have f of x equals g of x plus c. So we'll do that. So now we're going to suppose that I have two antiderivatives, and we're going to call them f of x and g of x. And we're going to define this function h of x, and it's going to be the difference of the two. So we're going to put h of x equals f of x minus g of x. Okay, so h of x is going to be differentiable because f of x and g of x, by definition of being antiderivatives, I can take derivative, and when I take the derivative, I should get f of x. Okay, so the goal here is I want to show h of x is a constant. If I can show h of x is a constant, then f of x minus g of x is constant also, which means they just differ by some constant. Okay, so we're going to let a and b just be elements of I, any arbitrary element, and I want to show that they're equal. Their outputs are equal when I plug them into this function h. Okay, and w log just means with loss of generality, so either a is less than b or b is less than a. The real numbers are a ordered field, so there's some sort of order to them. And since it's differentiable, we can use the mean value theorem that says there exists a c in that interval such that h prime of c is equal to the slope of the secant line connecting those 2 points. Okay, but we know that h of prime of c is going to just be equal to the derivative of f at c and g at c. So it's going to be equal to f of c minus f of c, which is going to be equal to 0. Well, derivative of big F is little f. The derivative of big G is little f because we suppose that they were both antiderivatives at the beginning. Okay, so this says that the slope of the tangent line at C is equal to 0, which also says the slope of the secant line is equal to 0. Okay, so if we multiply both sides by b minus a, we have h of a and h of b are going to be equal to each other. And since a and b were arbitrary, this tells me that h is constant. So it's going to be equal to some constant number, we'll call it c, some real number. Okay, but h of x is f of x minus g of x, and thus we have that f of x, it just differs by some sort of constant. Okay, and we observed this on the first slide that if I want to go backwards from a derivative to an antiderivative, I'm going to be off by a constant. We don't know what it is. We have infinitely many, uncountably infinite antiderivatives for a particular function.